Welcome to part 3 of the video podcast series on solubility product equilibrium here at Ontario High School. And we're going to do a problem that again involves the common ion effect, which are probably the most challenging of KSP problems. It's what we would say in the vernacular, it's time for a your turn problem. So this is the way this will work. The problem is here where we want you to calculate the solubility of calcium phosphate, which has a KSP value of 1.3 times 10 to the negative 32nd and a 0.20 molar sodium phosphate solution. So because this is your turn to do this problem, what I'd like you to do is write the problem down and then pause the podcast. You'll probably need to do that so that you can write the problem down and solve the problem, and then resume the podcast, and we'll go through the solution step by step, and we'll hope that your solution matches mine. So go ahead and pause and solve this problem. Welcome back. We'll go through the solution of this problem step by step. One of the first things that we like to do to help us is to write down the equation that represents the dissolving of the calcium phosphate in aqueous solution. So here we have Ca3PO4 solid, our double arrow representing that this is an equilibrium situation. And we form 3 calcium 2 plus ions for every 2 phosphate ions. Then we write our KSP expression is equal to the molar concentration of the calcium 2 plus raised to the 3rd power times the concentration of the phosphate ion raised to the 2nd power. We then look at setting up our ice chart. So our reaction is written, and then the initial, the change in the equilibrium concentrations. We know for every amount of calcium phosphate that dissolves, for every amount X, we would get 3X of the calcium ion and 2X of the phosphate ion. Our initial calcium ion concentration is 0. Our initial phosphate ion our initial phosphate ion concentration is 0.20 moles per liter. Our change is going to be plus 3x for the calcium ion and plus 2x for the phosphate ion. So at equilibrium, our concentration of calcium 2 plus would be 3x, and our concentration of the phosphate ion would be 0.20 plus 2x. We plug in these equilibrium concentrations into our KSP expression. So we have 3x cubed times 0.20 plus 2x. That expression squared is set equal to the KSP value of 1.3 times 10 to the negative 32nd. From the looks of this expression, you can see that solving for x is going to be a huge challenge if we are unable to make a simplifying assumption here. The good news is that our KSP value is so very small, 1.3 times 10 to the negative 32nd, that we can assume that 2x in the expression 0.20 plus 2x squared is so small in comparison to 0.20 that essentially when we add these together, because of significant figures, 0.20 moles per liter plus 2x is essentially 0.20. By allowing us to assume that, we can drop the 2x out of the expression and make this much simpler to solve for. So here we are using the assumption that 0.20 plus 2x is essentially equal to 0.20. So our expression simplifies to the KSP value of 1.3 times 10 to the negative 32nd is equal to 3x cubed times 0.20 squared. When we continue to simplify this, we have 1.3 times 10 to the negative 32nd is equal to 27x cubed times 0.04. When we go to solve for x, we first take our 1.3 times 10 to the negative 32nd and divide it by 0.04 and by 27. That isolates the x cubed on one side, and then we solve for x by taking the cube root of that, again simplified, 1.3 times 10 to the negative 32nd divided by 1.08. The cube root of that will equal x. So as we continue to solve for x, we take the cube root of 1.3 times 10 to the negative 32nd divided by 1.08 is equal to x, and our x value is equal to 2.3 times 10 to the negative 11th moles per liter. Once we know what our value of x is, we can calculate the changes in concentration and find our equilibrium concentrations of both the calcium and the phosphate ion. Our calcium ion concentration is equal to 3x, so we take 3 times 2.3 times 10 to the negative 11th moles per liter, and we end up with a calcium ion concentration of 6.9 times 10 to the negative 11th moles per liter. Our phosphate ion, we take our 0.20, we add 2 times 2.3 times 10 to the negative 11th. When you do that, because of significant figures, it's just 0.20 moles per liter, which proves our underlying assumption that 0.20 plus 2x is essentially 0.20. So here we are looking at our final concentration of calcium ion, 6.9 times 10 to the negative 11th moles per liter. Our final concentration of the phosphate ion being 0.20 moles per liter. And one of the interesting things that we can do is compare the solubility of calcium phosphate in just pure water rather than in a solution of sodium phosphate. And so this wasn't part of your your-turn problem, but I want to demonstrate it for you so that you can see how dramatically having a common ion present in the solution will affect solubility. So starting with the next slide, we'll work through that together. By now, this process should look very familiar to you. I've just written the same equation for the dissolving of calcium phosphate and set up for X amount of calcium phosphate, we get 3x of calcium ion and 2x of phosphate ion. We set up our KSP being equal to 3x cubed times 2x squared. So our KSP value of 1.3 times 10 to the negative 32nd would equal the product of 27x cubed times 4x squared, which is 108 times x to the 5th. So we take our 1.3 times 10 to the negative 32nd times, is equal to 108 times x to the 5th. So the 5th root of 1.3 times 10 to the negative 32nd divided by 108 will give us x, and 1.3 times 10 to the negative 32nd divided by 108 is 1.2 times 10 to the negative 34th. So the 5th root of 1.2 times 10 to the negative 34th is equal to 1.6 times 10 to the negative 7th moles per liter. Our calcium ion concentration is 3 times that value, 3 times 1.6 times 10 to the negative 7th moles per liter, which would give us an equilibrium concentration of calcium ion in pure water of 4.8 times 10 to the negative 7th moles per liter. Our phosphate ion concentration would be 2 times 1.6 times 10 to the negative 7th moles per liter, which would give us a value of 3.2 times 10 to the negative 7th moles per liter. I want to compare for you the amount of calcium ion that would dissolve with phosphate ion in pure water as opposed to the amount of calcium ion that would dissolve with phosphate ion in which there's already 0.20 moles per liter of phosphate ion present. So the amount in pure water was 4.8 times 10 to the negative 7th moles per liter. We're going to divide that by the amount of calcium ion in the 0.20 mole per liter sodium phosphate solution, which is 6.9 times 10 to the negative 11th. So when we find that ratio, we find that there are 6,956 times as much calcium ion in the pure water as in the solution containing the common phosphate ion. So approximately 7,000 times more calcium dissolves in pure water compared to dissolving in 0.20 moles per liter sodium phosphate solution. That's something that you want to embrace fully, is that the presence of a common ion dramatically decreases the amount that a slightly soluble salt can dissolve in water. That's the whole point of this. So, we are at the end of part 3 of the video podcast series that deals specifically with solubility product equilibrium here at Ontario High School. So I want to leave you with a quote from Marie Curie. Be less curious about people and more curious about ideas. I wish you well.